Hello again and welcome. We begin our journey into what is called inferential statistics. Now, to understand inferential statistics, we need to understand probability theory. You recall in the first session, we said that there are two types of statistics: descriptive statistics, which looks at what has already happened, but inferential statistics tries to look at what is likely to happen. To understand inferential statistics, we must understand probability. Now, probability, which simply the chance that something will occur in the future, underlies statistical inference. And we saw earlier that statistical inference is the drawing of conclusion from sample data. Now, if samples that are drawn from the population are random, are analyzed, and certain statistics are computed, such as the mean, then the mean value would depend on which sample is drawn. So it means that the value of the mean itself depends on chance, because the value the mean will assume depends on who is drawn in the sample. So to understand how to interpret sample evidence, we need to understand probability. So at the end of this session, you will be able to define probability and describe the classical, empirical, and subjective approaches to probability. And then you need to understand terms such as experiment, event, outcome, and then sample space. We'll also illustrate how to calculate probabilities applying the various rules like the addition, the multiplication rule. We'll introduce you to the concept of the tree diagram and how it can be used to compute probabilities. And then finally, we'll talk about how to determine the number of outcomes in an experiment using what is termed the multiplication, permutation, and combination formulas. So this is how the presentation is outlined. We begin with defining probability. Simply put, probability is the chance or the likelihood that something or an event will happen. Now, an extreme example, which is a bit callous, is to ask, what is the probability that somebody will die tomorrow, right? The person hasn't died, is still alive, but want to find the likelihood that somebody will die. In fact, sometimes these things are computed, and when you come to level 300 and study growth and development, you will discuss some of these things. Probability of an event may be defined in two ways. We have what is called the objective or the frequentist view, and it computes probability as the proportion of times the event happens in what is termed the sample space. And then we have the objective view, which is based on somebody's degree of belief about the likelihood of an event happening. Now, the objective view is divided into two: the classical view and then empirical approach. The classical view assumes that all outcomes of an experiment are equally likely and mutually exclusive. By equally likely, we're saying that each outcome has an equal chance of occurring, and then by mutually exclusive, we mean that if one outcome occurs, the other cannot occur. Now, what is good about the classical approach is that the probability of an event is said to be known a priori. In other words, it is even known before the experiment takes place. An example is that when you take a fair die and you roll it, as in a game of Ludo, then the probability that any number will appear is calculated as 1 over 6y, because there are 6 numbers, 1 through 6, right? And when you roll it, only one can appear. So the probability will be the number of times the number can appear, which is 1, divided by the 6 possible numbers. Another case is to look at tossing a coin. The coin has two sides, right? The head and the tail. when you toss the coin, you either get a head or a tail. And if you're interested in a tail, it can only appear once, right, when you toss it. But there are two possibilities, head or tail. So your probability is 1/2. And we're saying that with this classical approach, you don't even have to conduct the experiment because you know the outcome already. But the empirical approach, or what is also termed the relative frequency approach, is based on analyzing empirical data. So you collect data and then compute the probability of an event occurring. Now, normally the probability value is obtained as the long run rate of occurrence of the event. In other words, when the experiment is performed a large number of times. Now, there are some terminologies that you must understand. One, experiment, because I've been using, when we talk about an experiment in statistics, we're talking about an activity such as tossing a coin. So that's the experiment. And this activity or experiment has a range of possible observations or outcomes. So when you toss a coin, there are two outcomes. You either get a head showing or a tail showing. Now, the outcome means a particular result of the experiment. So in this case, you either have a head or a tail showing, but we're saying that we are interested in a head. So that's the result, a particular result of the experiment. And then the trial means that a single performance of the experiment. Because you see, when you toss the coin once, that is a trial. Another is to toss. So you can have a number of trials. You can toss the coin 10 times. So you have 10 trials. But when the experiment is performed on a single occasion, it's called a trial. And then the sample space refers to all possible outcomes of the experiment. And as I said, when you toss a coin once, the sample space is heads or tails. So there are two outcomes. And then the event is a collection of one or more outcomes. Okay, there's an outcome is a particular result, but we can have a collection of outcomes called an event. Now let's illustrate how the probability is calculated. Now if, let's say the event that we want to calculate the probability for, we call it A, and then S is the sample space, all the possible outcomes in the experiment. Then we write PA, meaning the probability of the event A, and it is equal to N in A over N in S. In other words, N in A means the number of times the event A occurs divided by the total number of outcomes in the experiment. So in our example, when you toss a coin once and we want to calculate the probability of heads, it is equal to 1/2, because when you toss a coin once, okay, the number of outcomes is 2, a head or a tail. So there are 2. But we want a head. A head can only appear once when you toss a coin once. So it is 1/2. Okay? What are the rules of probability? The probability of an event takes a numeric value between 0 and 1. The extreme scenario of 0 means that the event can never occur. And then the extreme value of 1 is when the event is certain to happen, right? Maybe the probability of tomorrow coming is certain, right? You know it will come. So the probability of the sun dropping from the sky onto the earth, you know it will not happen. So it's very remote. So you can say, but it lies between 0 and 1. So the probability of any event, which is likely, is greater than 0, but less than 1. And if you sum all the probabilities over all the possible outcomes, you must get 1. It cannot be greater than 1. We'll illustrate. And then the probability of not A, that is the event A not occurring, can be calculated as 1 minus the probability of the event A occurring. And we call probability not A the complement of the event A. Right? We should have cause to use these rules as we proceed. Let's illustrate. Okay, so let's use playing cards. I'm sure some of you like playing cards. Now let's consider a pack of cards. We know there are 52 of them, and they are grouped into what we call the diamond, the club, heart, and spade, right? And there are 13 of each because we have the ace, we have 2 through the number 10, and then we have the jack, the queen, and the king, and there are 4 times, so there are 52 in all. Now, if these cards are put upside down, flat, what is the probability of picking one card that would be a king of spades? So it must be a king and it must be a spade. A king and a spade, right? And we're saying that because there's only one card among the 52 that is a king of spades, the probability is 1 over 52. It is 1 over 52. And because there are 52 cards, for each of them, the probability of drawing them is 1 over 52. So if you sum 1 over 52, 52 times, it gives you 1. So the property that we looked at earlier. And then the second one, which says that the probability of not king of spades will be equal to 51 over 52. But you can write that as 1 minus the probability of king of spades, because probability of king of spades is 1 over 52. So 1 minus 1 over 52 gives you 51 over 52. So these are the ways to illustrate those properties that we looked at earlier. Now let's look at the addition rule of probability. Now often we are interested in calculating more complicated probabilities than what we've just illustrated. For example, you want to know the probability of drawing any spade, or the probability of throwing a double 6 with 2 dice, or the probability of a randomly chosen student from this class obtaining exam grade in Econ 214 better than a B, right? These are more complex events. Now, these events are called compound events because they involve more than one outcome. For example, in the third example that I gave, a student who should get a grade better than a B must either get a B plus or an A. So it involves more than one event, which is why we say they are compound events. Now, to apply the addition rule, you need to understand the concept of mutually exclusive and non-exclusive. I mentioned mutually exclusive earlier. And we say 2 or more events that cannot occur together are said to be mutually exclusive. So when you roll a die and you want to find the probability of a 5 or a 4 showing, we're saying these 2 are mutually exclusive because when you roll a die, 4 and 5 cannot appear at the same time. It's either one of them. So it's either a 4 or a 5. The 2 cannot occur together. But when they are non-exclusive, it means both events can occur together. For example, picking a king of hearts from a pack of cards. So in the first place, you can pick a king, right? And that king can also be what? A heart. So they can occur together. So let's illustrate the addition rule. Now the addition rule is also called the OR rule. So you want the probability of an event A or an event B or both. So to use that rule, we simply say it is probability of A plus the probability of B, right? Now this is termed the special rule of addition because it applies only to mutually exclusive events. Mutually exclusive events. So the probability of rolling a 5 or 6 on a single roll of a die, we are saying that it's 5 or 6. And the probability of 5 or 6 is simply probability of 5 plus the probability of 6. or probability of A plus probability of B, as we said. So the probability of a 5 is 1 over 6. We know it through the classical approach. Probability of 6 is also 1 over 6. So the answer is 1 over 6 plus 1 over 6, which is 1 over 3. And we are saying that this rule is applied to only mutually exclusive events. But look at what happens here. Suppose we take the case of playing cards, and we're saying we want the probability of a king or a heart. So we're saying that there are 4 kings, right? So these are the kings. A king of spades, a king of hearts, a king of diamonds, and a king of clubs. So there are 4 of them. So it is 4 over 52. Because there's an or here, we put our plus, right? Because the other is heart. The hearts are 13, so that is here. So it is 13 over 52. When you add, it's 17 over 52. But the answer is wrong. Why is it wrong? Because we have counted the king of hearts twice. Because king of hearts here counted as a heart, counted as a king. So there are only 16 dots highlighted, not 17, right? So to get around this problem, what we do is that it is the king, the probability of king or heart should be equal to the probability of king plus the probability of heart minus the probability of king of hearts. In other words, it is a king and a heart at the same time, right? So in general terms, we write this probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. A and B meaning that these occur together, right? Which means we're using the AND rule, which is the applies to multiplication. Now this is the general rule, whether it is mutually exclusive or non-exclusive. Because you know, when 2 events are mutually exclusive, that is, they cannot occur together, their probability of occurrence is 0. That is, probability of A and B equals 0 when A and B cannot occur together. And then if this part becomes 0, we get the previous result, right? So this formula can be applied to both mutually exclusive and non-exclusive events. Let's move on to multiplication rule. Now, to apply the multiplication rule, we need to understand what we call independent events and dependent events. Now, an independent event means that the occurrence of one event does not depend on the occurrence of another, okay? Or the occurrence of one event has no effect on the probability of occurrence of the other. So, for example, tossing a coin twice and obtaining 2 heads. So, when you toss a coin once, as we saw, you get the probability of head is half. But if you toss it again, the probability is again half. So, the probability of having a head on the second toss is not influenced by whether or not a head appeared on the first toss. But when events are dependent, then the probability of occurrence of one event does affect the occurrence of the other. For example, drawing 2 aces from a pack of cards, one after the other without replacement. So let's illustrate the multiplication rule. Now, when 2 events are independent, then the probability of event A and event B is simply the probability of A times the probability of B when they are independent. So, the probability of obtaining a double 6 when rolling 2 dice is the probability of a 6 and a 6. And since they are independent, it is probability of 6 times probability of 6, and it gives us 1 over 6 times 1 over 6, which is 1 over 36. That's the probability. But there's a slight complication when it comes to dependent events. Let's illustrate this. Let's say we want to calculate the probability of drawing two aces from a pack of cards without replacement. So first, you pick an ace the first time, and then the second time, when you pick the card, it must be an ace. Now, because there are four aces, when you pick any card, for it to be the probability of an ace must be 4 over 52. Now, that leaves 51 cards, of which 3 are aces. So the probability of drawing a second card, which is an ace, now is no longer 4 over 52, but now 3 over 51, which is different from the probability of drawing the first ace. So we say that these events are not independent, but rather they are dependent. Okay? So the probability of two aces must be the probability of drawing the first ace times the probability of drawing the second ace, which is different from the probability of the first ace. And your answer is 1 over 2 to 1. So the second probability, that the probability of drawing the second is 3 over 51 that we obtained, is called the conditional probability. It is on condition that an ace was drawn first. So this value is conditional, right? So conditional probability is said that written as the probability of drawing a second ace given, this vertical line is said to say given that an ace is drawn first. And we'll say it is conditional probability. In general terms, it is written as probability of B given A. In other words, the probability of an event B occurring given that event A has already occurred. So consider this. Let's say we talk about the probability of a second ace given that not an ace was drawn on the first. Then the probability of not ace on the first leaves 51 cards, of which 4 are aces. So the probability of ace on the second draw, given that not an ace was drawn first, is equal to 4 over 51, which is different from the 3 over 51 we got when the ace was drawn first. So probability of second ace, given that not ace first, is not equal to probability of ace second, given that ace first, because this one was calculated as 3 over 51. So we say that they are not independent events. So the general rule for multiplication, therefore, must be the probability of A and the probability of B is equal to the probability of A multiplied by the conditional probability of B. For independent events, the probability of B given A is the same as the probability of B not A, and it is equal to the probability of B. So the probability of A and B becomes the probability of A times B, as we saw earlier. So with examples, you will understand these things. Let's wrap up by looking at determination of number of outcomes. Now, consider that we wish to find the probability of one head in 2 tosses of a coin. So we toss a coin twice. We want to find the probability of one head. We can use a trick to solve this problem. For example, we want the probability of one head in 2 tosses. We can write it as this: probability of head and tail, or probability of tail and head. Because you see, when you toss a coin the first time, you either get head or tail. But you get head first, the tail could be second, or you get tail first, the head could be second. So this because of this, or we can write it as probability of head and tail plus probability of tail and head, because if whether you get probability of head and tail, when you toss the coin twice, the head appears once. In this first case, the head appears first, but the tail appears second. Or this one, the tail appears first, the head appears second. In either case, the head appears once. So, because this is head and tail, we can apply the multiplication rule, and then we can also apply the multiplication rule because it's tail and head, but the or here means we use the addition rule. So because we know the probabilities a priori as half, it is half times half plus half times half. It gives us what? Quarter plus quarter and half. We can put this in what is called a tree diagram, because we're saying that when you toss a coin the first time, you either get a head or a tail. But if you got a head first and you toss it again, you either get a head or a tail, right? But if you tossed it the first time and you got a tail, you can toss it again and get a head or a tail. So this gives us the roots through the tree diagram. It means that when you toss a coin first, the probability of head is half, and the probability of tail is half. So when you sum, it's 1. Now, having gotten a head first, when you toss the coin again, the probability of head is half, and the probability of tail is half. Or having obtained a tail first, when you toss it, the probability of head is half, the probability of tail is half. So this gives us the possibilities. That is, when you toss a coin, you can have 2 heads, or you can have 1 head, 1 tail, but with the head coming first, the tail second. Or you can have 1 head, 1 tail, but this time the tail comes first, or the head comes second. Or you can have both being tails. So these are the outcomes. And the probability of having head is 1 over 4, because it is head and head. So 1 half times half, 1 over 4. This is head and tail, 1 over 4. This is tail and head, 1 over 4. And this is tail and tail, 1 over 4. But because we want only 1 head, getting 1 head is either it comes as head and tail, or tail and head. So it is or plus, all right? So you add half, quarter and quarter. So the probability of 1 head still gives you your half, as we got before, all right? So when you have an experiment, you can draw this tree diagram to get your probability. But the point is that, what about if we wanted to calculate 3 heads and 5 tosses, or 30 heads and 50 tosses? The tree diagram cannot go on the screen, right? It will go through the roof. So we need to find a formula for calculating probabilities, and there are techniques for doing this. Now first, let's look at the multiplication formula. Now the multiplication formula is used to find the total number of outcomes for 2 or more groups of objects. So let's say that, I'll give you an example very soon. Let's say that there are n1 objects of one kind and n2 of the other kind. Then there are n1 times n2's 2 ways of selecting both. In other words, assuming there are 2 boys and 3 girls, okay? So one kind is boy and there are 2 of them, and one kind of girls, there are 3 of them. We want to find out how many ways can a family have 1 boy and 1 girl. It is simply 2 times 3, which is 6, right? So there are 6 ways in which you can have 1 boy, 1 girl. So we can do it to k groups of objects. So if there are k groups of objects, it is n1 times n2 times up to times nk, where n1 is equal to n2 is equal to nk. That is when you have the same number of objects in each group, then the formula is simply n raised to the power k. Now let me give you another practical example. You know, a few months back, last 2 years or something, MTN was saying that they have reached the 10 millionth customer. You remember that? Okay, how did they determine that? You see, if you take your mobile phone number, apart from the code of 024, there are 7 other digits, right, at the end. Those last 7 digits are used to generate the mobile phone numbers. But the digits are 10, 0 up to 9. Okay, so of each kind, there are 10 of them. Okay, so N1 is 10, N2 is 10, up to N7, right? So to find the maximum number of customers MTN can have using 024 means that it is 10 raised to the power 7, which is 10 million. As soon as you hit that number, you cannot get an extra customer. That's why they changed to 054, right? So that's what it means. So it shows us how many ways of selecting one object each from 2 or more groups. So this is how to illustrate. Then we come to what is called the permutation formula. Whereas in the multiplication formula, there are 2 or more groups. When it comes to permutation, there's only one group, and we want to find out how many subsets we can generate from that group. So an example is saying that the number of ways of having 3 girls in a family of 5, right? So let's say generally we want R items to be selected from a set of n objects at a time where R is less than or equal to n. Then we are saying that any particular sequence of these R items is called a permutation. And you obtain it using this formula. So we're saying that selecting R objects from a set of n, written as NPR or n permutation R, is equal to this formula, where this is called n factorial over n minus r factorial. So this symbol, n, with this symbol is called n factorial. And n factorial means that it's the product of all the integers up to and including n. So n factorial is n times n minus 1 times n minus 2 up to 1, right? And we're actually talking about the positive integers. So if you say 2 factorial, it is 2 times 1, you end there. 3 factorial is 3 times 2 times 1, you end there. 4 factorial is 4 times 3 times 2 times 1, you end there. Then you evaluate the result. So let's say we want to find the different ways of having 3 girls in a family of 5 children. 5 permutation 3. So 5 factorial is 5 times 4 times 3 times 2 times 1. Divided by n minus r. So in this case, it is 5 minus 3, which is 2. So it's 2 factorial, 2 times 1. It gives us 60. So there are 60 ways in which you can have a family of 5 children containing 3 girls. Okay? Now, what is crucial is that in permutation, the order of arrangement is important. We are not looking at the individuals, but rather the positions they occupy. So, for example, an arrangement where Kofi comes before Amma is different from an arrangement where Amma comes before Kofi. So, if you have Kofi and Amma, or even if they're the girls are 3, so you have Abigail, Bernice, and Charity. Okay? So even though there are 3 girls, if Abigail is first and Bernice is second, even though it's the same individuals, when the roles are reversed, it is the same, it is a different permutation. So we are saying that with permutation, it is the positions occupied that is important and not the individuals. Now with the combination formula is the same as the permutation of the number of ways of selecting a subset of objects from a given set of objects. But here we are not concerned about the order of arrangement. Once it involves the two individuals, it's okay. If both Kofi and Amma are there, fine. We don't care who comes first, because in permutation, when Kofi comes first, it is different from when Amma comes first. But in combination, we don't care. Once it is Kofi and Amma, whoever comes first, we don't care. And the formula is n combination r, and it is equal to n factorial divided by r factorial multiplied by n minus r factorial. And the factorial is as previously defined. So 3 girls in a family of 5 children is 5 combination 3. It gives us 10. So there are 10 ways of having 5 children with 3 girls, but without regard to the order in which they come. Now, with the combination formula that we've learnt, we can use it to write the formula for calculating probabilities. For example, the probability of 1 head in 2 tosses of a coin. We can write this as the probability of 1 head, and it is equal to the probability of 1 head and 1 tail in that order. So head comes first, tail comes second, multiplied by the number of possible orderings, or the number of ways that events can occur. The number of ways in which you can get 1 head in 2 tosses of a coin. And since we're using combination, we're saying that the probability of head is half times the probability of tail is half times 2 combination 1. You toss the coin twice, you won 1 head, right? So 2 combination, and it's equal to 1 over 4, because half times half is 1. And this 2 combination 1 is equal to 2. It gives you an answer of half. What we got previously. Okay, so we can use the formula now to calculate the probabilities, not a tree diagram. Now, to be able to do this, we need to learn about the binomial distribution, which we shall discuss soon. So we bring our discussion of probability to an end here, which is the foundation for further work. We'll be discussing other probability distributions soon. Thank you very much.